All right. So we have a good mathematical ability to model concentration, temperature. We can talk about activation energy. We understand that there are steric effects. You know, we have a good sort of mental picture of experimentally how all these things play in. The last sort of piece to this puzzle, the last piece to understanding what's going on is really looking at why. What kind of theoretical underpinning, what kind of explanation based on collisions of molecules do we have for this whole mathematical construct, for all this experimental data? And the big question that certainly sits at the back of a lot of our heads is, why does the stoichiometry, the number of particles we see reacting in the equation, not matter? How come all of this stuff seems to be completely unrelated to the number of particles that we see, that we know from stoichiometry are reacting? Those ratios for the number of reactants, how come they don't match with the collisions that we're talking about? And the answer, the thing that we really need to understand is that on a microscopic nano level of looking at individual molecules and of the collisions, that the chemistry that we deal with at the stoichiometry level is not the same as what actually happens in the reaction, in the realm of individual molecules smacking into each other. The stoichiometry doesn't work. The stoichiometry is a bigger view. It's a look at an overview, a starting and ending view, not a how did we get from the starting point to the ending point. What was the reaction mechanism? What series of elementary steps took place? What series of small collisions actually happen in a larger reaction? Okay? Here is a chemical reaction. Nitrogen dioxide can react with carbon monoxide. If we study this reaction, we can find that the rate law for this reaction depends on the concentration of the nitrogen dioxide squared, and is independent of the concentration of carbon monoxide. As long as you have some, the rate of the reaction doesn't depend on the carbon monoxide. That clearly doesn't match with the stoichiometry. If I look at the stoichiometry, I think the nitrogen monoxide and the carbon monoxide should be the same. Their importance in how fast the reaction happens looks like it should be the same. If we go through and study this in much more detail, if we go through and we do really quick time resolution studies of what's happening, we see some other intermediate complexes being formed, other intermediate molecules that come and go very quickly in the reaction. So it looks like from studies that two nitrogen dioxide molecules smack together to form a nitrogen trioxide molecule and a nitrogen monoxide. And then it looks like the nitrogen monoxide molecule reacts with the carbon monoxide. So because the actual mechanism, the way that the reaction happens, involves these intermediates, it is these elementary steps that we need to study if we want to truly understand why the rate law is what it is. Elementary steps are steps where the molecularity, the number of molecules reacting, the stoichiometry, is the same as the order of the rate law. So here, for this reaction, I have two nitrogen dioxide molecules reacting. The rate law is NO2 squared. In this step, I have a nitrogen trioxide molecule reacting with a carbon monoxide. And the rate law is first order for both of those. This is a reaction. Both of these are what we call elementary step reactions because what molecules are reacting, what we call the molecularity, matches the rate law. If I add these two reactions together, I get the overall reaction. That is one of the criteria for choosing a reaction mechanism. If you add the reaction mechanism, if you add the mechanism all together, you should get the overall reaction. First check. Check number 2. The slow step, or what we call the rate determining step, needs to match the experimentally determined rate. So in this reaction, this first step is slower, happens at a significantly slower rate than the second step. This one is fast. As soon as the NO3s are produced, they get reacted with the carbon monoxides. So the rate determining step is the slow step of the mechanism. And its rate law is what determines the rate law of the whole thing. Okay? So if you have a series of steps, the slowest step of the whole batch is what determines how fast the whole reaction can take place. The analogy I like to think about here is if you've ever been to Krispy Kreme donut store. Have you seen the machine they have for making donuts? Takes up most of the building, right? Takes up most of their little donut store. They have a section where they mix up the batter and they dump it into a machine. And the machine forms the donut rings. And then it puts them onto this conveyor belt system that goes up and down, up and down, up and down in a warm room so the donuts can rise. And then the donuts come out of the warm room and they get dumped into the river of boiling oil. Okay? They literally have a river of oil that flows along with the donuts. Then they have this little flipper machine. The donuts come up and they get flipped over. And then they go up onto a conveyor belt and they go under the waterfall of icing. Okay? And then they go around and dry and then people pull them off. Each part, each step of the machine can handle donuts at a certain rate. The rising machine can say, let's say it can make, 1,000 donuts an hour. But the dough forming machine can form 2,000 donuts an hour. The ribbon of oil, the river of boiling oil can do 500 donuts an hour. And the waterfall of icing can do 750 donuts an hour.
I don't understand it. I think we should overdone.
Okay? If you look at the whole process, the rate at which you can produce donuts is controlled by the slowest step. The river of boiling oil can only do 500 donuts. It doesn't matter how fast all the other pieces can go. Your whole thing is controlled by the slow step. It's the exact same thing with these types of reaction mechanisms. It doesn't matter how fast the NO3CO step goes. If the step that produces what it needs is slow, that's the speed that the whole mechanism can travel at. That's why this rate law here is what determines the rate law for the overall reaction. It's the river of oil in our donut creation. It's the slow step. Okay? So, typical type of problem involves being given information about reaction rates. Okay? You check to make sure that this cancels out. Okay, to give you your overall reaction. Thank you. Or? Yep. And you can go now if you want to see your counselor. Yeah, either way. I don't know. Yeah. Okay, that's fine. All right, so these things cancel out, right? Now notice that some of these things, the NO2 is what we call, that's a reactant, right? That's still a reactant. But this NO3, notice it doesn't show up in the overall. It cancels out completely. We call that an intermediate. Intermediates can be identified because they are produced in early steps and used up in later steps. The other thing that will show up in reaction mechanisms that you won't see in the overall is a catalyst. How would a catalyst act differently than an intermediate? It's not used up. Well, it doesn't show up in the overall, so it does cancel out. It still cancels out of the reaction mechanisms. But catalysts start as reactants and end up as products. So they cancel out, they go in and they come out. Whereas intermediates are produced and then used up. Okay? You need to be able to identify catalysts versus intermediates. Catalysts go in as reactants and come out as products. They still cancel from the overall. Intermediates they do. Catalysts speed up chemical reactions. Okay? But they don't show up in the overall equation. Intermediates are necessary for the reaction to take place. They are molecules that are formed in one step of the mechanism and used up in a subsequent step. One last thing. If this second equation here was the slow step, what would be the rate law for the overall reaction? So, the rate of the second one, that's going to control it. But here's a problem. NO3 isn't in our overall reaction. I would substitute the NO2 because it's the NO2, the rate of this NO2 that controls the concentration of the NO3. So you substitute in, for the intermediate, you substitute in something that controls it, that are reactants. So the rate here, okay, if we substitute in the NO2, then the overall rate would be what? Okay, we would substitute in for the NO3 if this was the slow step. I just substituted in this part here for the NO3 because it takes 2 NOs, this rate law, 2 NOs to 1 NO3. I used the stoichiometry to say, hey, for every 1 NO, I need 2 NO2s to produce it. So that the concentration of the NO3 is controlled by the concentration of the NO2s, or is equivalent to it, if I wanted to express it in terms of my reactants that are in the overall reaction. So just watch out for that little trick, okay? This is not. We go through and we determine this rate experimentally to be NO2 squared, which tells me that this one is the slow step. This rate law is the slow step. It's what determines the overall reaction. I was saying, hey, if this had been the slow step, how would this rate law, the overall rate law, be different?
So is it in the second rate law, is it squared because it's...
There's 2 of them. There's 2 of them. And this is an elementary step. So the rate of NO3 production is controlled by the NO2 squared. Well, we know which one's a slow step because which one matches the overall. Or they can tell you, like in this example, they'll say slow, fast, fast. I'm not saying that it would be impossible, but no, typically that's not the way it's done. So, very typical type of reaction. Here, type of problem. We have hydrogen reacting with nitrogen monoxide to produce nitrogen gas and water. They are telling us what the rate law is. NO2 squared, H2. That is the experimentally determined overall rate law. Which one of these 3 mechanisms could be the true mechanism? What are the 2 things we have to check? Do they cancel out? So go through. Do they cancel out? Figure it out. Okay, take a minute, look at this. Do they cancel out? So does this one match? Yeah, it's the exact same equation. Now we have to look here and we say, you got to look, this cancels with that. Oxygen cancels here. We've got 2 H2Os, 1 nitrogen, 2 hydrogens, 2 NOs. This cancels out. This works. Okay? And then what about here? N2O cancels out. 2 hydrogens, 2 NOs, 1 nitrogen, 2 waters. So all 3 of these have the same overall reaction. That's the first thing we check. What's the second thing we need to, what's the other criteria we got to look at? Does the rate law agree? Does the rate law for the slow step match the overall? So you need to go through and say, hey, what's the rate law here? If this is an elementary step, we know that the rate law is the same as whatever the molecules are, whatever the coefficients are. So the rate law here is hydrogen squared, nitrogen monoxide squared. In an elementary step, what we're saying is these are the particles that have to collide. The likelihood of 4 particles running into each other all at the exact same time is very, very small. Biparticle, 2-particle collisions is the norm. 2 particles colliding off each other, that can happen. That's relatively common. 3-particle collisions are possible, but really rare. Statistically, getting 3 particles to collide at the same point in time, very, very unusual. Okay? Now, uniparticle, just 1 particle just falling apart, that can also happen. Okay? That can also happen as well. But usually, almost all elementary steps are 2 particles colliding together. Which steps? So step number 1 was, does it add together to give the overall? So we checked that. We said, okay, it adds together to get our overall. Second, we want to say, does the rate law match? So I look at the slow step. In this case, there was only 1 step. And I look at the rate law. What would be the rate law for this slow step? H2 to the first, NO to the first. Right? The coefficient is 1 and 1. So those are just first order, first order. Does that match? Now, where's the slow step here? Okay? The first one, and again, I have H2, but now there's 2 NOs. This is 3 particles colliding together. Unusual, sure, but possible. So the rate law would be H2 NO squared. No, it's NO squared. The coefficient becomes the exponent in the rate law. It is possible, but unusual. No, it's very rare. Statistically, 3 particles colliding at the same time is very, very unusual. So, do you have methods to determine the overall from experimental data? Yeah, you got the method of initial rates and integrated rate law. Those are the 2 ways you could figure this out experimentally. It's unusual for them to combine 2 problems like that, but it's possible.
For us to figure out the rate for ourselves?
Yeah, you can do that. You know how to do that. We've done a whole bunch of problems like that. That's the method of initial rates, where we found out N and M. That's figuring out the rate law.
But what if you know it's wrong, but...
What if you know what's wrong?
I mean, what if you know, like, what if they do combine them and you know the initial rate is wrong, but you have a match in the 3? Could you do, you know how,
So this is determined experimentally, right? This overall rate law is determined by doing chemical experiments to figure it out. So that's usually right. And then you're looking for a match in a series of potential mechanisms. And that doesn't guarantee you that mechanism, right? You actually need to go through and look for some of these products in your reaction at very short time scales and stuff like that, doing special studies to verify your reaction mechanism in the real world. For our purposes, they're only really going to ask you to check, does it add together to give you your overall? And does the slow step rate law match the overall? That's your 2 criteria that you got to worry about.
how come we can't determine the overall rate law just the same way we did the slow one?
So, all of these mechanisms are based off what we call elementary steps. Steps where the stoichiometry matches the molecules actually colliding. in this stoichiometry, do we actually have 4 particles colliding? No. It looks like we actually have 3 particles colliding and 1 step, and then the results of that reacting some more. And in fact, even that's very unusual. So anytime you see more than 2 particles is a reactance, you know, the coefficients of more than 2, there's probably some other stuff going on. And even then, even if you just had, like, remember we saw the NO and the CO? That reaction actually had some other mechanism that takes place. That's very common. So you have to conduct a lot more deeper studies to find out what molecules are actually colliding. And there are ways to do that, not at this level, but if you go and become a chemist.
So when you have 3 particles collide, the coefficients of the exponent.
No, in any elementary step, the coefficients are the exponents. That's the definition of the elementary step, because the molecules, guys, the molecules that are in the reaction are the molecules that are colliding. And it's the rate laws dependent upon what's colliding, what molecules are actually colliding together. Okay? All right. That's it. You now know everything there is to know at this level about reaction rates. How do we control how fast a reaction happens? How can we speed it up? What happens as the concentration changes? How does time, temperature, activation energy, all that stuff factor in? We understand that chemical reactions happen through a series of steps usually, and it's those steps that determine the rate law.
We can keep Betsy safe.
We can keep Betsy safe. So if the reverse reaction happens, then we do chapter 13 and learn all about equilibrium. That's our next unit.